Good morning, class. Today we're going to talk about Chapter 8, which is all about gases. Let's talk about the properties of gases first. So generally, molecules with fewer than 5 atoms from the first 2 periods in the periodic table are gases at room temperature. Please remember, periods are rows, groups are columns. I know it's been a while since we've talked about the periodic table. In addition, the following are also gases: H2, N2, O2, F2, and Cl2, also known as hydrogen gas, nitrogen gas, oxygen gas, fluorine gas, and chlorine gas. We call these diatomic molecules. Di meaning 2, atoms, diatomic. Also, oxides of the nonmetals on the upper right corner of the periodic table, such as carbon monoxide, carbon dioxide, nitrogen oxide, nitrogen dioxide, sulfur dioxide, and sulfur trioxide. And then finally, the noble gases: helium, neon, argon, krypton, and xenon. So those are the types of gases that we're going to be dealing with this chapter. Now let's talk a little bit about kinetic molecular theory. Kinetic molecular theory states that a gas consists of small particles, hence the fewer than 5 atoms, that move randomly with high velocities, meaning they're moving very, very fast in random patterns. They have very small attractive or repulsive forces between the molecules, which is why they're not a liquid or a solid. They're just not attracted to each other. Number 3, they occupy a much larger volume than the volume of the molecules alone, meaning if you have a container with gas molecules in it, the molecules will spread to fill the container, but most of the space in the container is just empty space. It is not closely packed with molecules. This is why we can easily walk through air. Number 4, the gas molecules are in constant motion, moving rapidly in straight lines until they strike the nearest wall. Then they bounce off the wall and move in a new direction, straight line until it hits something else. Then they bounce off that wall, and so on. So they're in constant motion, moving rapidly in straight lines until they hit something. And finally, they have a Kelvin temperature proportionate to the average kinetic energy of the molecules. Well, what in the heck does that mean? So let's break it down. Kelvin temperature. We haven't used it much this semester, but Kelvin temperature and Celsius temperature are very similar. One is just offset from the other. The reason that Kelvin temperature is used in this chapter and not Celsius is that we do not want negative numbers. Putting a negative number into an equation to solve for a pressure or a volume could give you a negative volume or a negative pressure, neither of which exist. So we use the Kelvin scale, which has no negative numbers. So number 5 said we have a Kelvin temperature proportionate to the average kinetic energy of the molecules. Anybody remember what kinetic energy is? The energy of motion. So what number 5 is saying is that the higher the temperature, the higher the kinetic energy of the molecules. Or the higher the temperature, the faster the molecules are moving. The lower the temperature, the slower the molecules are moving. So that is number 5 broken down into easier to understand terms. In order to describe gases, we use 4 properties. We use pressure, volume, temperature, and amount. The last 3 are ones we should be familiar with: volume, temperature, and amount. Pressure is probably a new one. Remember that volume is a measure of the amount of space occupied by something, and you should be familiar with those units, the liter and the milliliter. Temperature, we just said we're going to use Kelvin, right? And temperature is the determining factor of the kinetic energy and rate of motion of gas particles, meaning it tells you how fast they're moving. Okay? So again, we're going to use Kelvin, not Celsius in this chapter. And then amount is always measured in moles, which we should be familiar with from the last chapter. Grams is also a measure of amount. However, you will never use grams in any of the calculations. You will always convert to moles. Okay? Pressure, again, is the new one. It's the one we haven't really had a chance to talk about yet this semester because we've been mostly dealing with liquids and solids. Pressure is the force exerted by a gas against the walls of the container. And there are many, many, many units of measurement available to us to measure pressure. We have atmospheres, millimeters of mercury, torr, Pascal, kilopascal. Anybody know how many pascals in a kilopascal? Right, that's one of those conversion factors you should know. There are 1,000 pascals in a kilopascal. For those of us who grew up here in America, PSI, pounds per square inch. Although, of course, we don't use American units here in chemistry. We use SI units. But in case you're wondering what our unit of measurement is, it's the PSI. Okay, moving on. The volume of a gas is always the same as the volume of the container it occupies. And you may remember this from the previous chapter when we talked about the properties of solids, liquids, and gases. We said that a gas had a variable volume, and that's because the volume of a gas is always the same as the volume of the container it occupies. If you increase the size of the container, right, it increases its volume. If you decrease the size of the container, you decrease the volume of the gas. So it's variable. And we typically measure this in liters or milliliters. The volume of a gas also increases with an increase in temperature if the pressure remains the same. So the volume of a gas increases with an increase in temperature if the pressure does not change. Okay. Temperature. The temperature of a gas relates to the average kinetic energy, again the average energy of motion of the molecules, and is measured in the Kelvin temperature scale. When the temperature of a gas is decreased, the molecules have fewer collisions. When it's increased, the molecules have more collisions, which kind of makes sense if you think about it. If you've got a bunch of molecules moving around in random straight line motions in a container, if they're moving slowly, they're less likely to bump into each other. If they're moving rapidly around the container, they're much more likely to run into each other. Pressure. Again, pressure is a measure of the gas particle collisions with the sides of a container and is measured in units of millimeters of mercury, torr, atmosphere, pascals, kilopascals, pounds per square inch, lots of units. The only unit whose conversion factor you need to know is between pascals and kilopascals. Another type of pressure is called atmospheric pressure, and that's when the gas particles in the air exert pressure on you and I. We call this atmospheric pressure. So that is what you feel in the air around you as the gas particles are striking you. And this atmospheric pressure changes with variations in weather and altitude. On a hot, sunny day, the mercury column rises, indicating a higher atmospheric pressure. So again, as millimeters of mercury, a unit of pressure, increase, we have a higher atmospheric pressure. On a rainy day, the atmosphere exerts less pressure, which causes the mercury column to fall, indicating fewer millimeters of mercury and a lower atmospheric pressure. There were several scientists who studied relationships between the various units in gases. The first scientist we're going to talk about is Boyle. Boyle studied the relationship between a pressure and a volume of a gas, and he discovered that it was an inverse relationship. Anybody know what an inverse relationship is? It means that when one variable goes up, the other variable goes down. So since Boyle studied pressure and volume, essentially what he said was that if you increase the pressure, you decrease the volume. If you decrease the pressure, you increase the volume. So again, this is an inverse relationship. When one goes up, the other goes down. And the formula that he came up with is P1V1 equals P2V2. We are going to become very familiar with this formula. Okay, so as we can see, we have a couple of examples here. We have a P1V1 equals 8 atmospheres times 2 liters. Total is 16 atmosphere liters. If that is true and you have the pressure to 4 atmospheres, right, 4 atmospheres, then the volume must double, right? If you have one, you double the other. Okay. Yes. Chemistry linked to health. So this is one of the ways in which we try and link this to the real world. Boyle's law explains how we breathe. When we breathe in, our lungs expand, which means the volume increases, right? If the space in your lungs increases, the volume is what's increasing. When that happens, the pressure in your lungs decreases. Again, because Boyle's law is an inverse relationship. When the volume increases in your lungs and the pressure decreases, the air outside of your lungs flows towards the lower pressure in your lungs, allowing you to breathe. Now let's try some other real-world examples. Freon 12 was used in refrigeration systems. We want to know what is the new volume of an 8-liter sample. So 8 liters is a measure of what? 8 liters is a measure of volume. Initially at 500 millimeters of mercury. Millimeters of mercury means that we are dealing with a unit of pressure. So this is P1. After its pressure is changed. So we have a new pressure. Our new pressure is 2200 millimeters of mercury at constant temperature in moles. So we have a V1, a P1, and a P2. And we want to solve for V2. So P1 times V1 equals P2 times V2. So let's put this in our equation here. We have P1 is 550, keeping track of our units, mmHg, times V1 is 8 liters, equals, whoops, okay, and I'm running out of room here, it equals V2, which we don't know, times, and actually I'm going to rewrite this down here because I've run out of room, 550 mmHg times 8 liters equals V2, which we don't know, times P2, which is 2200 millimeters of mercury. To solve this, we multiply 550 millimeters of mercury times 8 liters, so 550 times 8, and then we divide by the 2200 to get our final answer. Divide by 2200 to get 2. Our millimeters of mercury, once we divide out, cancel, and we are left with a unit of liters. So 2.0 liters is our final answer. So let's try a new example. A sample of oxygen gas has a volume of 12 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36 liters at constant T and N? So we have a volume of 12 liters, V1, and we have a pressure of 600 millimeters of mercury, that's P1. We have a P2, we have a V2 of 36 liters, and we want to find P2. So if we place this in our equation, we have 600 mmHg times 12 liters equals 36 liters times P2, which we don't know. So again, if we place this in our calculator, 600 times 12 liters is 7,200, and then we divide by our 36 liters, we get an answer of 200 millimeters of mercury. Okay. All right, let's talk about a new law. We also had this scientist named Charles who studied the relationship between temperature and volume. So now, instead of looking at the relationship between pressure and volume, we're going to look at the relationship between temperature and volume. According to Charles, if we increase the temperature of a gas sample, kinetic molecular theory states that the motion, or kinetic energy, of the gas particles will also increase. If the amount and pressure of the gas is held constant, the volume of the container will increase. In Charles' law, the Kelvin temperature of a gas is directly related to its volume. Pressure and moles of gas are constant. When the temperature of a sample of gas increases, its volume must also increase. This is because we are now dealing with a direct relationship and not an indirect relationship. So, according to Charles' law, if you increase the temperature, you increase the volume. If you decrease the temperature, you decrease the volume. Charles' law in mathematical formula is V1 over T1 equals V2 over T2. Okay, Charles' law, V1 divided by T1 equals V2 divided by T2, because this is a direct relationship and not an indirect relationship like the previous one. So let's try some examples. A balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon at constant pressure in moles? So we have a volume of 785 milliliters and a temperature of 21 degrees Celsius. We are changing our temperature to 0 degrees Celsius, and we want to know what is the new volume. So if we put this in our equation, we have 785 over 21 equals V2 over 0. Anyone know what happens when you try and divide by 0 in a mathematical equation? You get an error on your calculator, right? And further, if we were to multiply both sides by the 0 to get rid of it, anytime we had a 0 degrees Celsius, what would our volume be? Our volume would drop to 0. But we know that that isn't true. If you have a balloon with air in it and you take it outside in 0 degrees Celsius weather, your volume does not drop to 0. This is why we use the Kelvin system. The Kelvin system does not have these zeros. Anybody know how to convert Celsius to Kelvin? So let me erase what we have here, right? Because we're going to have to change this. Okay. Anybody remember how we convert Celsius to Kelvin? So the formula is really simple. Kelvin is equal to Celsius plus 273. That is because the system is the same, it's just shifted a little bit. So if we wish to convert our temperatures into degrees Kelvin, we simply add 273. So let's rewrite our equation, this time putting in the Kelvin numbers. So we have 785 divided by, well, let's see here, 21 plus 273 should give us 294 Kelvin. This was milliliters. Keep track of our units. V2 we don't know. And 0 plus 273 is just 273. So let's find what our new volume is. 785 divided by 294 gives us 2.67. Then multiplying both sides by the 273 to get it out of the denominator gives us a new volume of 729 milliliters. This makes sense, right? We said that if you increase one, you increase the other. Also, the reverse is true. If you decrease the temperature, you would expect the volume to decrease. So we went from 785 milliliters, our initial volume, to a new lower volume of 729. Again, when you're working these problems, particularly on a quiz or on a test, try and make sure that your answers make sense, right? We want to make sure that if we know the law and we know what happens, that we're getting an answer that makes sense within the problem. Let's try another one. A sample of oxygen gas has a volume of 420 milliliters at a temperature of 18 degrees Celsius. At what temperature in degrees Celsius will the volume of the oxygen be 640 milliliters? So we have 420 milliliters. Hold on a second, I'm just going to change this to a slightly smaller size. See if this helps. Okay, 420 milliliters is a volume. That's V1. Temperature, 18 degrees C, but of course we're going to turn that into Kelvin, right? So 18 plus 273 is 291 degrees Kelvin. Is our T1. Okay. At what temperature in degrees C, so we don't know T2, will the volume of the oxygen be 640 milliliters? So we know V1, we know V2, we know T1, we're looking for T2. So let's put this into our equation. We have 420 milliliters divided by 291K equals 640 milliliters divided by T2. Let's solve our equation. 420 divided by 291 gives us 1.44 on the left. 1.44 equals 640 divided by T2. Now here is the most common mistake I see on exams. Students attempt to multiply both sides or divide both sides by 640 to isolate the T2. The problem with that approach is that the T2 is in the denominator. In order to solve this equation, you need to get the T2 by itself, and you need to get it out of the denominator. The best way to do that is to multiply both sides by T2 to get rid of it, and then divide both sides by the 1.44. So T2 equals 640 divided by 1.44. Here we go. And the final answer is 444. But again, what units is this in? Because it's not in Celsius. Remember that we converted to Kelvin to start the problem. If the question asks for the units in Celsius, how do we get back? So we've talked about how to go from Celsius to Kelvin. How do we go the other way? Well, if this is our equation to go from Kelvin, or rather Celsius to Kelvin, to go the other way, we would subtract 273. So 444 minus 273 tells us that our new temperature is 171 degrees Celsius. Does this answer make sense within the context of our problem? So what is our volume doing? We went from 420 milliliters to 640 milliliters. So we increased our volume. Therefore, what should happen to the temperature? The temperature should increase, right? If you increase the volume, you should increase the temperature. So we went from 18 to 171. Does that make sense? Yes, it does. It seems a bit high, doesn't it? 291. Did I make a math mistake here? Let's go back over our numbers real quick. 420 divided by 291. It's 1.44. Multiply both sides by T2 to get it out of there. Divide both sides. Yep, that's right. Just seemed a bit high for a moment. Okay. Our next law relates temperature and pressure. Okay, we're going to relate temperature and pressure. This is Gay-Lussac's law. By the way, I'm not really concerned with you memorizing the names of the laws. I want you to understand how to use them. Memorizing the name of the scientist that goes with the law does not bother me. So Gay-Lussac's law. Gay-Lussac's law says that when the Kelvin temperature of a gas doubles at constant volume and amount, the pressure also doubles. So again, this is another direct relationship. When one goes up, so does the other one. And again, we are talking pressure and temperature. P1 over T1 equals P2 over T2. P1 over T1 equals P2 over T2. So this law looks very similar to the last law, except now we're relating pressure and temperature. So again, the pressure exerted by a gas is directly related to the Kelvin temperature of the gas. Volume and amount of gas are constant. So let's look at a couple of examples. Example 5 in your notes says a gas has a pressure at 2 atmospheres at 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius with constant volume in moles? So what are we given? We have 2 atmospheres. That's a pressure. And we have 18 degrees Celsius. Of course, we're going to convert that to Kelvin. So 18 plus 273 tells us that we have 291. Kelvin equals T1. Let me see here. What is the new pressure? So we're looking for a P2 when the temperature is 62 degrees. So we've increased the temperature. 62 plus 273 is 335. So T2 is 335 K. Okay, let's put this in our equation. We have P1 is 2 atmospheres divided by T1 is 291 equals P2 we don't know divided by T2 is 335. Now before we solve this, what do we expect to happen? What are we doing to our temperature? We're increasing our temperature. So what should happen to the pressure? Remember that this is a direct relationship. So if you increase one, you should increase the other. Since we are increasing our temperature, we expect to see a larger pressure. So almost put 20 in there. 2 atmospheres divided by 291 Kelvin gives us 0.00687. Then multiplying both sides by 335 gives us a new pressure. P2 is 2.3 atmospheres, which is exactly what we expected to see happen. We expected to see the pressure increased, and it did. Let's try another example. Example 6 says a gas has a pressure of 645 torr, new unit here. So we have torr now instead of atmosphere. That's our pressure 1. At 128 C, let's convert that into Kelvin right now. 128 plus 273 gives you 401. That is our T1. We want to know what is the temperature in Celsius if the pressure increases to 824 torr. So we have a P2 and we don't know T2. So again, let's put this in our equation. We have 645 divided by 401 equals 824 divided by our question mark. Again, don't forget that the question mark is in your denominator. Right? It's in your denominator. So please do not multiply both sides of this equation by 824. So let's see here. We have 645 divided by 401 gives us 1.61. 1.61 equals 824 over x, or question mark, or T2, whatever variable you want to call it. Multiplying both sides by the x gets it out of the denominator, right? And then dividing both sides by 1.61 gets the x alone. So multiply both sides by x to get it out of the denominator. Right? And then you get 1.61x equals 824. So to get rid of the 1.61, we divide both sides. 1.61, 1.61. So 824 divided by 1.61, oops, I almost put 1.64 in there, gives us 512. Is this what we expected to happen? Well, first, let's check and make sure we got our answer in the correct units. Well, this is in Kelvin. The question asks for us in Celsius. So again, if Kelvin is equal to Celsius plus 273, Celsius must be Kelvin minus 273. So 512 minus 273 gives us a much more appropriate temperature of 239 degrees Celsius. Again, does this make sense? We have, what have we done? We have increased the pressure from 645 to 824. Therefore, we expect the temperature to rise. And it has. We've gone from 128 to 239. So our answer makes sense. And we're in the correct units. Okay, so the last part of Chapter 8, Part 1 is vapor pressure and boiling points. Let's talk briefly about those. When liquid molecules, now granted we're talking about gases this chapter, but when liquid molecules with sufficient kinetic energy, or sufficient energy of motion, break away from the surface of a liquid, they become a vapor. A vapor is a gas, which is of course why we're talking about this. If this occurs in an open container, all of the liquid will eventually evaporate, which is why if you leave a glass of water out on a table for long enough, eventually the glass will be empty. In a closed container, the vapor accumulates and creates a pressure called vapor pressure. So imagine, instead of an open glass on a desk somewhere, you have a closed container. Right? And some of the liquid molecules escape to become a gas. With time, as more and more molecules escape to become gas, they build up a pressure, right? Those gas molecules are moving. As they're moving, they're striking the walls of the container, creating a pressure. We call this pressure vapor pressure. A liquid exerts its own vapor pressure at a given temperature, and it boils when the vapor pressure becomes equal to the external pressure pressing down on the system. So when the vapor pressure has built up to equal the external pressure pressing down on the system, the liquid boils. This concludes Chapter 8, Part 1. Thank you, and I hope to see you for Chapter 8, Part 2.